So let's see how the pillbox would look in example 3 here. So an infinite plane carries a uniform surface charge sigma. Find its electric field. So we have, some plane that kind of goes everywhere. I'll just kind of draw. And charge density sigma. And so we're going to draw a pillbox somewhere in this plane. Goes down and it intersects that surface, and then we continue downwards that way. Now the electric field is going to point away from this surface, so we have to figure out how much charge we enclosed. Well, the charge we enclosed is just simply the area here, so we have some area on top. So Q enclosed equals the area times the charge density. And now we have to figure out, well, this is a rather trivial integral. So E vector dot dA vector is going to reduce to the magnitude of E times dA. And we're using a flat surface on the bottom and the top. We're assuming none of that passes out the side, which is a rather good assumption. So we basically get the magnitude of E times, what's the surface area? A is equal to the charge enclosed divided by A over epsilon naught times sigma. The A's cancel, and so the electric field is equal to sigma over epsilon naught, and it points in the normal direction from the surface. Again, this is so easy, it's almost like trivial, laughable to think about that. Now, one interesting thing is that this one doesn't depend on how far away from the surface you are. And it's not obvious at first why that is, but a good way to think of it is imagine that you had like a telescope. And so you're looking through this telescope at this infinite surface, right? So here's you, and you're holding this telescope, right, which is basically like a cone, and you can see like a circle, right? And you're a distance from that of r, right? And that circle has an area that's proportional to r squared, right? However far away is some factor of r squared. And it just turns out that this area that you see with that telescope, even though you're growing as you go away, well, the weakness of it is proportional to r squared, so these r squareds happen to cancel out. And that's really a good way to look at it. And if you imagine that this telescope gets wider and wider until you're looking infinitely, then it makes sense that you're basically, as your distance increases, the amount of charge it's pulling on you also increases, but its weakness also decreases in proportion to how much is pulling on you. So the interesting result is that when we did the circle, let me pull that out. What the circle looked like. So we had r squared. When we did the, I feel like we've done something wrong here. When we did the cylinder, well, this was actually not, a uniform cylinder would fall off over 1 over r. We didn't have a uniform cylinder. And this is a uniform plane, and so it falls off with nothing. It doesn't fall off at all. Which, I guess if you think about it, kind of makes sense. This is the zero-dimensional point source. The cylinder is a one-dimensional line source, and this is a two-dimensional plane source. So